The next thing we're going to take a look at is looking at molar mass and how to molar mass and how to convert between the amount of a substance, meaning grams, and the number of particles of a substance. But before we go on with that, I want you to take a few minutes and look at this question. I'm not going to give you the answer now. Normally, if we were in the classroom, I'd tell you guys, guys, work on this together. And what do you think? Let's see. All right, so everyone on your own, I want you to think about this question, right? Methane undergoes combustion with oxygen according to the following equation. Which of these statements are true? There are 4 moles of hydrogen atoms in 1 mole of methane molecules. There are 1.2 times 10 to the 23 hydrogen atoms in 1 mole of methane molecules. In 18.02 grams of hydrogen, there is 1 mole of oxygen atoms. 2 moles of methane will produce 4 moles of carbon dioxide molecules. And based on the reaction as written, water vapor is produced. So, take a minute. Take a minute to think about what it is, and we're going to come back to this later. So, all right, so we're going to come back. Don't worry that you don't have the answer just yet. You might end up changing your answer when we come back to it. All right, so we already know about the molar mass. The molar mass is we are adding up all the masses of all the atoms in every in the compound, right? And instead of using AMUs that we see, wrong con, I can't with you. Where we see on the periodic table is AMU, you're going to change that to grams per mole. So we've had some practice doing this when we were looking at unit 6 with solutions. Now, we will have some calculations using the molar mass and Avogadro's number, right? So the molar mass equality is converting from moles to grams, right? And those conversion factors, if we're looking at methane as an example, 1 mole of methane is 16.05 grams of methane, right? So we have that conversion factor, 16.05 grams per 1 mole. And also 1 mole of methane can also mean that it's 6.02 times 10 to the 23 molecules of methane, right? So we have two different conversion factors, but what is the common denominator, I'll say? What is common for both of these equalities? What's the common thing that we see for both of these? Right, moles. So can I just go from grams straight to molecules? Can I convert directly from molecules to grams? Can I do that?
Yes.
Nope. You surely cannot. You cannot. You would actually have to first convert to moles, then to molecules. So yes, Stephanie, moles is the middleman. I like that one. I like that. Yes. So you have to use moles as the middleman. You cannot go directly from grams to molecules. You have to always get to moles. Moles is a way for us to level out the playing field, we'll say, right? Because 1 mole will always be 1 mole. It's always going to be 6.02 times 10 to the 23 molecules. But depending on the compound, it's going to be a different number of grams. So we can only convert between moles to moles. We can't convert between grams and grams. We can't convert between molecules and molecules. We have to use moles to get through there. And grams of the compound is the atomic mass. The molar mass, not the atomic mass. because it means I have 16.05 grams in a whole mole. Now, atomic mass would be 16.05 AMU. So we're going to use the conversion factor depending on which direction we're asking for. So if I'm going from grams to molecules, I would have to have moles on top. If I was going from molecules to grams, then moles would be on the bottom. It all depends on the direction for which we're going in. As all conversion factors are, it depends on what we're starting with and where we need to go. So let's take a look at this question. A tiny pencil mark just visible to the naked eye contains about 3 × 10⁻17 atoms of carbon. What is the mass of this pencil mark in grams? So let's start off solving these problems in a systematic way. We're always going to consider what we were given. We were given 3 × 10⁻17 atoms. And what do we need? We need the mass in grams. So what are our conversions, right? If we're starting out with atoms, we need to get to moles. As Stephanie said, moles is the middleman. And from moles, we need to convert to grams, right? So there are 2 steps to this problem. The first step, we're going to have to use which conversion? Are we using the molar mass or are we using Avogadro's number?
Avogadro's number.
We're using Avogadro's number because it's particles to moles, right? And how would we set this up in order for us to get moles from that calculation? Would moles go on top or would it go on the bottom?
On top.
Moles would go on the top, all right? So our second conversion we need now is from moles to grams, and we would need the molar mass. Now, the molar mass is grams per mole, but what direction would we have our conversion? Are we going to leave it as grams per mole, or is it going to be moles per gram?
Grams per mole.
Yep, we're going to make it grams per mole. All right, so now let's set up our problem. So here is where dimensional analysis that we learned way back in Unit 1 becomes very important. Because if you do a bunch of calculations, you're number 1, you're going to round off too much. And number 2, you get lost with what answer was what value was what. So it's really just simpler and more direct to do the dimensional analysis, where we start off with what we're given. We want to know the grams of carbon. Starting off what we're given, 3.3 × 10⁻17 atoms, we're going to now use our first conversion, 1 mole per 6.02 × 10⁻23 atoms. And then we're going to use our second conversion, which is going to be grams per mole. Notice that our atoms cancel out and we get left with moles. Then our moles cancel out and we end up getting left with grams. So that now gives us the answer. So we end up with 5.99 × 10⁻⁶ grams. And because we started with just one significant figure, we have to round off. Here we go with that 0.99 again. We have to round off to 6 because we only had one significant figure, okay? Remember, this is being recorded. You can always go back and check it. Let's move on to the next question. All right, pseudoephedrine hydrochloride is a nasal decongestant commonly found in cold medication. How many molecules of this compound are in one tablet that contains a dose of 30.0 milligrams? So let's systematically consider what we're given and what we need and how we need to get there. So we're given that we have 30 milligrams. Wait. Molar mass is in grams, right? So we got to remember that. We got to think about that. And what we need is the number of molecules. So what steps are we going to make to solve this problem? Well, the first thing we need to do is convert from milligrams to grams. Why? Why do we need to convert from milligrams to grams? And it's lowercase m, not big M. Why do we have to convert? Right, Patrick, because molar mass is in grams. All right, next, we're going to convert from grams to what? Who's our middleman? That's
Moles.
Moles. And then from moles, we're going to go to our answer. What do we need? We need our answer in molecules. All right. So I've got 3 arrows, meaning that I've got 3 conversions that I need to do. Right. So number 1, we need a metric conversion between milligrams and grams. Right. And we're going to have to make sure that grams are on top and milligrams are on the bottom, because grams are what we need. Notice that for every conversion, each step that you make, you put what you need on top and what you need to cancel out on the bottom. So number 2, our next conversion is going to be molar mass. And remember, we're going for moles. So moles is going to be on top. Our last conversion now is going to be Avogadro's number. And because molecules is what we want, we're going to put molecules on top. Everybody following me? We good? Give me a hands up. All right, cool. All right, here we go. So we're starting with what we need. We need the number of molecules. So Avogadro's will be molecules, atoms, ions, anything that is a particle, particles. All right. So we start with the 30 milligrams. We're going to use our first conversion, which was 1 gram per 10 to the 3 milligrams. What's another way that we can write 10 to the 3?
1,000.
We could write 1,000 there as well. And it's easier to put 1,000 in your calculator. The next conversion we're going to use is our molar mass. The molar mass is 201.69. So for this type of problem, you would have to calculate the molar mass first, unless it's given to you. And then the last conversion we need is our Avogadro's number. Okay. So how do I put this in my calculator? I would put this in the calculator as 30 times 6.02 divided by 1,000 divided by 201.69. It's really important that you multiply all the way across the top, divide all the way across the bottom. That way your answer would come out right. We're gonna cancel out our magnesium, cancel out our grams, and cancel out our moles. So because I put my answer, my calculation into the calculator as 30 times 6.02 divided by 1,000 divided by 201.69, this is what I end up in my calculator. There's probably some more digits, but because I need 3 significant figures, I already rounded my answer off here, right? So now I move my decimal place over 1, 2, 3, 4. So being that my coefficient got larger by 4 decimal places, then my exponents has to get smaller. Thanks, Sha. My exponents has to get smaller by 4 decimal places. All right. So we end up with 8.95 times 10 to the 19 molecules. What is the mass in grams of 3.2 times 10 to the 22 molecules of water? Let's see how we solve this problem. All right, we want to know the number of grams. So we start off with what we were given. We were given the 3.2 times 10 to the 22 molecules. Our first conversion is going to be what? What's the first conversion factor that we have to use? Since we're starting with molecules, we have to use what conversion? Molecules to moles, right? And we're going to put moles on top because moles is always the middleman. We always got to get to moles before we can get to anything else. And we need to cancel out molecules. And then the last thing that we need to do is to put in our molar mass. Remember, memorize the molar mass of water. 18.02 grams per mole. Memorize it. Put that on your memorization list. Okay? That's one of the things that you should probably just memorize for this class, just for the sake of not having to calculate it all the time, because we're going to use it a lot. Our molecules cancel out, our moles cancel out. We put in our calculator 3.2 times 18 divided by 6.02, and we end up with 9.6 times 10 to the minus 1. So to just make it so that we don't have to use scientific notation, we would use D, 0.96 grams. All right, so we've only been talking about, right now, we've been talking about the amount of a substance, right? We're going from the number of moles of a substance to the number of particles of a substance, right? Using the molar mass. Now, when we look at a compound, when we look at a chemical formula, right? We're looking at aspirin. Aspirin has, for each molecule, aspirin has 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms, right? That is the number of atoms that we would have in one molecule. But what now if we had a whole mole of aspirin? Well, now that formula that we have here, we can now say that for every mole of compound, we have 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. So within 1 mole of this compound, I would have the same number of moles as I have of atoms for each element, all right? So for each formula, for each molecule, we would look at these subscripts as atoms. But if we're looking at a mole of substance, we're going to look at these subscripts as moles, right? So those subscripts can mean the number of atoms or the number of moles of each element in the compound. Just depends on what we're looking at, whether we're looking at a molecule or we're looking at a mole. So if we're looking at aspirin, we can come up with conversion factors based on 1 mole of substance, right? So if I have 1 mole of aspirin, I have 9 moles of carbon. So I can make this conversion factor of 9 moles of carbon per 1 mole, or 1 mole per 9 moles of carbon. And we can do that for each of the atoms in the molecule. Okay, so here we have 4 moles of oxygen per 1 mole, and we have 8 moles of hydrogen per 1 mole. Why were these written in either direction? Remember, conversion factors can be, being that it's equal to 1, right? Remember, we start off with 1 mole, so 9 moles of carbon per 1 mole of aspirin, that is equal to 1. We can swap the conversion in either direction. So the subscript could mean the number of moles of that element or the number of atoms within that compound. So it depends on what we're looking at. If we're looking at one molecule or one unit, we're looking at the atoms. If we're looking at one mole, then we would be looking at the number of moles of atoms, right? So this means 9 moles of carbon atoms are in 1 mole of aspirin. That's what that means. So where's my pen? So what this means is that there are 9 moles of carbon atoms per 1 mole of C9H8O4. So that's what that means, 9 moles of carbon atoms. Oh, I lost my mouse. Where did it go? My mouse is missing. Okay. Here we go. So let's do some practice with the same aspirin molecule. How many atoms of oxygen are in 0.15 moles of aspirin? Well, we want to know the number of atoms, and we're always going to start with what we're given, right? And for this, we're going from moles to atoms per compound, right? So we need 2 steps. We start off with 0.15 moles of aspirin. Notice that I actually write this. If you came to office hours, I would still write everything down because I want to make sure that I'm canceling out the right things, right? So for every 1 mole of aspirin, I'm going to have 4 moles of oxygen, right? Sorry about the change of writing here. And then I'm going to have, for every mole of oxygen, I'm going to have 6.02 times 10 to the 23 atoms. So what were our 2 conversions? We had our first conversion was our formula, right? And our second conversion was Avogadro's number, okay? So that was our second. So here we have number 1, number 2. Notice that our moles of aspirin cancel, our moles of oxygen cancel, and we're left with 6.13 times 10 to the 23 oxygen atoms, right? So we were going from moles of substance to moles of atoms. I don't know why this pen does this. Atoms to the molecules of atoms. All right, and that was 1 and 2. Right. So the maximum dose of sodium hydrogen phosphate that should be taken in 1 day for use as a laxative is 3.8 grams. How many moles of sodium ions and how many total moles of ions are in this dose? So now we're not looking at a molecule, we're looking at an ionic compound, and we can say, so what are our 2 ions? We've got the sodium ion and the HPO4 ion. We end up with, we have 2 sodium ions and we have 1 HPO4 ion per formula unit, right? So this question is asking us the number of sodium ions and the total moles of ions, the total moles of ions. So this is 2 separate questions. And how do we solve this? What we were given is 3.8 grams, right, of sodium hydrogen phosphate. And we need to know the number of moles of sodium ions and the number of moles of total ions. So we're going from the grams of A, or which is our sodium hydrogen phosphate, to the moles of sodium hydrogen phosphate, right? Then we're going to the moles of B, which is our ions. So A is going to be sodium hydrogen phosphate, and B is going to be either our sodium ions or our total ions. So we've got 2 conversions that we need to use here. Our first conversion is going to be our molar mass, going from grams to moles of the sodium hydrogen phosphate, which we're given. Our second conversion is going to be our formula unit. Right? And it's the molar ratio of our formula unit to get to the final answer. So to find out the number of moles of sodium ion, we start with what we're given, 3.8 grams, times number 1, which is our molar mass, because remember, we can't go straight from grams to moles. We can't go from grams of something to the ions of something without going first through moles. So 1 mole of sodium hydrogen phosphate is going to be 142 grams. Notice that our grams will be able to cancel out. And then there are, as I said previously, 2 moles of sodium ion for every mole of sodium hydrogen phosphate. Our grams cancel out, our moles cancel out, right? And I get 0.054 moles of sodium ion. Now, our second question is asking for the total number of ions. Let's go back up here. Total moles of ions. How many ions do we have per formula unit? How many ions do we have per formula unit? I know class is almost up, but I want to finish this one question. How many moles do we have per formula unit? You guys writing that in the chat? Yes, 3. We have 3 total moles. 3 moles of ions. So we're going to use the same steps, right, that we used to solve originally. So let me erase my other stuff, right? So I get 2 sodium plus 1 hydrogen phosphate. That gives me 3 moles. All right, so I want to know total ions. I start once again with 3.8 grams times the molar mass. It's the same thing. Now we're going to say we have 3 moles of ions per 1 mole of substance, right? The only thing that we changed here is the number of ions that we were looking at. And we end up with 0.80 moles of total ions. All right. So that's it for today. We're gonna pick up on Thursday with and don't forget, I still haven't forgotten the question that I asked you earlier. We're gonna get back to that on Thursday. We still have some more practice to do before we go back to answer that question. So review this material before you come to class on Thursday. Make sure you review the PowerPoint so that you can have a clear idea of how to solve these problems. And the homework for 7B is all this stuff, all of this, including the, 7B is all these types of calculations. So if you need help doing your work, make sure that you join office hours. I have my office hours today at 11:30. If you still need help, make sure you join any of the other office hours as well.